Recording in progress.
All right, guys, we'll go ahead and get started. Let's see, make sure. Oh, good. Okay. Oh, and maybe it would be helpful if you guys could see me too. Perfect. All right. So we left off last night with the heat diffusion equation, and which is what you're looking at here. So it's remember it's just a glorified energy balance, just rearranged. And so we did problem 13 just required us to sort of simplify that general governing equation, the heat conduction equation. And so we're going to do the same thing with 14. All right, so we're starting with the three-dimensional heat transfer, heat conduction or heat diffusion equation, same thing. We want to write down the one-dimensional transient heat conduction equation for a long cylinder with constant thermal conductivity and heat generation in its simplest form. So let's go ahead and write some stuff here. Move some stuff around here. All right. So there's my cylinder. And I do have that. I do have heat conduction, so I'll put a little Q dot there, right? Yep. And they do tell me that K is a constant, right? Constant thermal conductivity, transient. They do tell us it's one-dimensional. And as far as, well, what dimension are we talking about? If this is the Z direction, this is the radial direction. All right.
What does transient mean again?
Transient just means things are changing with respect to time. So anything that you see d dt, right, derivative of whatever with respect to time, it would be equal to 0. So we just want to find, I guess, the simplified, I'm going to call it the simplified heat conduction equation. That's all. Right. Don't really know what I need to assume, but we'll just kind of put it there anyway. All right. So we looked at the heat conduction equation in Cartesian coordinates. We also have it in cylindrical coordinates. Your book also has some problems with spherical coordinates, but we're not going to do that, just Cartesian coordinates and cylindrical coordinates. So it looks kind of similar. So on your equation sheet, page 2, upper right-hand corner, you'll see the heat conduction equation written in cylindrical coordinates. So we're going to write that as well. All right. A little bit. There we go. All right. So I have 1 over R. Yeah, it's fine. Then I have the partial. Oof, I don't like that. Sorry. All right. So the partial of R dt dr plus 1 over R squared. Second partial derivative of temperature with respect to V plus second derivative of temperature with respect to the Z direction plus my Q dot over K, which is equal to my 1 over the thermal diffusivity, and then I've got the partial of the temperature with respect to time. All right, so they represent the same kind of thing. So the stuff in green, the first 3 terms, represent the energy transferred by heat conduction in the R direction, in the direction of phi and z. So let's kind of look at what we're talking about when we talk about phi. So if I looked at this cross-sectional area, phi would be like this. That's what I'm talking about, that angle right there. And most of the time we can kind of ignore this. And in this class, we're always going to ignore it. The only time you wouldn't be able to ignore it is say that, I expose this side to something hot and this side to something cold, then the temperature is going to be dependent on that angle, right? But most of the time that's not the case. So, not the case. I'm actually going to delete that guy right there, and I'm going to cross this guy. Oops. Cross this guy out. Oh, there we go. And then the fact that it says that it's a long cylinder here, the fact that they say it's a long cylinder indicates that we really don't have to worry about the temperature gradient in the Z direction, right? But it will mostly be something we're going to have to worry about in the radial direction. So you're thinking about where the temperature is changing, where the temperature gradient is going to be biggest, right? And if this Z, if that it's a long one, well, the denominator is going to end up being very small. So those two terms are going to go away. We have heat generation, says it's transient. I guess that's really all I can get rid of. That's it. So, all right, and so this is going to be the name of the game. We're going to be applying our heat diffusion equation to various situations and trying to apply boundary conditions, and then solve this differential equation to get the temperature distribution throughout that medium. So, but before we do that, let's work a couple of more simple ones, or at least one simpler one right now. So this one's, so we have, at a given instant in time, the temperature distribution within an infinite homogeneous body is given by the function. So they've already given us the temperature distribution, right? So the heat conduction equation has already been applied. We've gotten a temperature distribution. And this temperature distribution is, again, at a particular instant in time. So maybe at another instant in time, that temperature distribution might be different. We don't know. Might be steady state, it might not be steady state. So we're gonna look at that. And it says, assuming constant properties and no internal heat generation, we want to find the regions where the temperature changes with time. So what we're really looking at, we're going to be finding the regions. When we say regions, we're looking at coordinates, right? So values of x, y, and z, where that temperature dt, the derivative of temperature with respect to time, where it's not equal to 0. That's where we're looking at, right? Where things are changing with time, where it is not steady state. All right. Oops. All right. Right, so I don't know, constant properties. Yeah, they threw it in there, so I'll throw that in there, sure. Constant properties. All right. So what we're going to do is we're going to start by applying our heat diffusion equation. Again, heat diffusion, heat conduction, same thing. All right. So we've got term representing conduction in the x direction, in the y direction, and in the z direction, right? And then, yes, I know this Q dot, they did tell me it was going to go away, right? They said no heat conduction. That's fine, or no heat generation, but I'm going to put them in there anyway and show that I'm crossing them out. All right. Perfect. All right, so I'm going to cross this guy out, and now I'm left to look at that. Okay, now I actually have to evaluate. I'm going to rearrange this and put this guy here as dt, and that's going to be equal to that guy, thermal diffusivity, times second partial derivative with respect to x, second partial derivative with respect to y, and same thing with respect to z. And because I have that equation, temperature is a function of x, y, and z, I can evaluate each of those second derivatives. So let's do that. The class this morning kind of laughed when I said, "Do you remember how to evaluate those?" So let's just do it together, yeah. So, all right. So if I took the first derivative of this guy right here, first derivative with respect to x, I treat everything that's not x kind of like a constant. So the derivative would be 2x, and then that negative 2y, well, the derivative of that with respect to x is just 0. Same thing for z squared. The derivative of negative xy would be negative y, and then the derivative of 2yz with respect to x is 0. And so if I take that derivative again with respect to x, all I have is 2. So let's start plugging that in. All right, so I have 2 plus something. All right, so now we're gonna, at least keep that equation in the frame. So dt dy. All right, so derivative of x squared with respect to y would be 0. The next one is going to be what? Negative 4y. Negative 4y. Derivative of z squared with respect to y is 0. Derivative of negative xy with respect to y would be negative x. And then the very last one is going to be 2z, but I guess it doesn't really matter, because when I take that derivative again, oops, wrote that wrong. It's just going to give me negative 4. All right, let's keep on going. Do it with respect to z. All right, so with respect to z, I'd have 2z plus 2y, and then I take the derivative of that again with respect to z, I would just get 2. Okay. All right, so that's just going to give me 0. So what does that mean? So we were asked to find, well, what values of x, y, and z could I plug in and end up getting a non-zero value for dt dt? And there's nothing, right? So all we could say is it's steady state. Again, the reason why we're saying it's steady state is because for all values of x, y, z, that dt is equal to 0. It doesn't matter what values I plugged in. Okay.
Can you scroll up for just a sec?
Mm-hmm. That. All right. So let's start talking about, I think we're going to start talking about boundary conditions. So kind of going back to thinking about actually applying and using that heat diffusion equation to calculate or to derive temperature distribution within a medium. So let's do that now. So this is on video 2.4 if you want to see it a little bit more. But basically what we have, if you have a differential equation, if it's got a time component, you're going to need an initial condition, right? If it's got a time component. And all that's going to be is that t at some initial t is equal to 0, just equal to, we'll call it ti, t initial. All right. And then we get the boundary conditions. So I'll kind of underline this guy and this. All right, so boundary conditions. And we've got several different types. So let's see if I can. There we go. So here's my plane wall. There's x. Here's x equals 0. Here's x equals L. All right. Oops. I'll bring you over here because I think I'll use you again. All right. All right, so the first boundary condition is a constant surface temperature. So that's case number 1, constant surface temperature. So maybe this side is at some T1, and the other side is at some T2. Or maybe I've got them, maybe I've got the blue on the left-hand side, the cool side on the left hand, and the hot side on the right-hand side, whatever. And so we're going to need to define boundary conditions at the boundary. Great. So the boundary conditions would be, all right, so T at x equals 0 is equal to T1, and T at x equals L is T2, right? Easy peasy. Other type of boundary condition that we would have, there we go. I'll copy that one down here before I mess it up too much. All right, so the other boundary condition that I might have is, say I had an applied heat flux to one side. So we had a problem like this, I think maybe day 1, where you have some Q applied. Oops. And I'm going to put it in terms of flux just to eliminate the area part of it. And I know that that flux has to be equal to this flux. I realize I drew like a whole bunch of arrows for the applied flux, and I'm drawing one arrow over here. Don't read into it. It's just, I'm just trying to say that it's applied uniformly, that flux is applied uniformly to that left face. So if it makes you feel better, put a whole bunch of other little red arrows. But this would be Q by conduction. I know there's a Q by conduction because if I did an energy balance on that surface at x equals 0, remember a surface is two-dimensional, and so there's no volume to store energy or for there to be energy generation. So whatever is coming in has to be going out. And so, well, then my boundary condition here, right over here, here's boundary condition 1. There was a boundary condition 2. Here over here, I'm just specifying a boundary condition on one side. So it would just be, so let's put a couple of little hash marks right there to indicate that it's a flux. My applied heat flux has got to be equal to the heat flux due to conduction at X equals 0. And we can further specify that because we are familiar with Fourier's law. So Fourier's law says this would be negative K dt dx, and it's all at X equals 0. All right. So let's go to next guy. All right, so option number 3, we have a convective boundary condition. And actually we've got kind of 2 cases here that we could look at. Maybe I have convection on the right-hand side. That might be a little bit more familiar. So, right, you have some convective condition over here. So you know that there's got to be convection. Okay. And if you did an energy balance on that surface at X equals L, whatever is going in has to be going out. Okay. I'm going to put a little Q conduction, little hash marks there. All right. And so my boundary condition would be, all right, Q conduction at X equals L. So it's negative K dt dx at X equals L. Perfect. And I know that has to be equal to what's going out, which is going to be the Q by convection. So H times, and when you're applying Newton's law, like the way that I've drawn that arrow there, it's as far as like, is it T infinity or is it T of the surface? Start with the, it's a pointer. No, it's not. All right, we'll start with this side of the arrow. So that's T surface, and then you'll end up with T infinity at that side of the arrow. So it'll be T at the surface being the temperature at X equals L minus T infinity. I'm saying that because let's say that I had convection on the other side. And so maybe I have Q by convection here. Okay. And if I did an energy balance, well, that just means that whatever's going into that surface has to be going out. And so if I apply my energy balance, it's going to be, all right, so it's going to be the convection at X equals 0. And when I do, which temperature goes first, it's going to be the T infinity, right? Basically, you got to start on that end of the arrow and end up at the pointy end. So T infinity minus T at the surface, which is T at X equals 0. And then you've got negative K dt dx, and this guy is going to be defined at X equals L. I'm sorry, not X equals L, X equals 0. Sorry about that. So when you draw your arrows, as long as you're consistent, especially like with Newton's law, as long as you're consistent, the math is going to tell you if you had your arrow drawn right or not. So if I ended up calculating a negative value for this Q convection, then I know, oh, actually the arrow was supposed to be flipped the other way, and that's okay, right? So just be consistent and the math will tell you what's going on. So both of these are convective boundary conditions. All right. We also have adiabatic surface. That's another one. Adiabatic meaning no heat transfer. in thermo, when we talked about adiabatic, when we said adiabatic, we were usually talking about a process. So adiabatic process has no heat transfer, which would be terribly uninteresting in this class. But here we would be talking about just a surface. So it's fine. There we go. So maybe I throw some insulation right here. So that's my adiabatic surface. And so all you would be able to say, well, if I did an energy balance at x equals 0, probably need to define that. Here's 0, here's L. If I did a surface energy balance, remember, whatever is going in has to be going out. And at x equals 0, nothing's going in because it's an adiabatic surface, no heat transfer. So what you could say is that for your boundary condition, you would just say 0 is equal to negative k dt dx at x equals 0, or you could just leave that and you just say that's dt dx at x equals 0, right? Because there can't be, I can draw an arrow here, right? Q by conduction, but right there at x equals 0, there's nothing. All right. So now I want to talk about thermal symmetry and how you can make your boundary conditions kind of work out nicely mathematically. So let's put it right here. So thermal symmetry. All right, there we go. So remember we had, I can't remember if it was, I guess we're really on day 3. I think it was day 1. We had a problem where the plane wall was a thickness of 2L. It said it's 2L. And so I said, well, that's kind of a heads up to take advantage of thermal symmetry. We're going to do that here. So let me kind of, there's the midpoint. There we go. All right, so I'm going to say this is x equals L. This is, or x equals 0, x equals L on the right, x equals negative L. And let's say that we have some sort of heat generation going on. All right. So if I wanted to look at the temperature distribution within that medium, it would look, well, forgot to say, we've got convection on the sides. Same convective boundary condition on the side, right? Same temperature, same convective heat transfer coefficient. So same conditions on the side. Well, your temperature distribution is going to look like that. So if you've solved for the temperature distribution to the right of x equals 0, you've solved for it on the left because it's just the mirror image, right? Okay. So let's say I didn't think about that. I didn't think about, well, that could be, I could take advantage of thermal symmetry there. Oops. I'm going to show you at least 2 ways that I could talk about those boundary conditions. So I'd have 2 of them. Boundary condition 1. Actually, before I even write boundary condition 2, let's make sure I give enough for boundary condition 1. All right, so it looks like, okay, we've got heat generation. So in my mind, I could kind of figure out which way the heat's going to be flowing. It's going to be going out, right? You got energy generation, keeping the temperature in the middle high, and then you've got this cooling convective boundary condition on the faces. So, I know probably I'll have Q convection going out right here. I'm also going to have Q convection going out right there at x equals negative L. If I did a surface energy balance, there we go. Get this a little. So this would be my Q. Let me zoom in here because this would be my Q by conduction at x equals L. And on the left-hand side, this would be my Q by conduction at x equals, right, this is x equals L. This guy is x equals negative L. So, okay, perfect. So let's do our boundary conditions here then. So for the first boundary condition, let's do it at, I don't know, x equals negative L. So I would say, all right, so at x equals negative L, I'd have Q by convection. And the way that I would define that Newton's law of cooling, so it would be H times, and it would be at the beginning of the arrow, the temperature at the beginning of the arrow, and it'd be T at x equals negative L minus T infinity. And this would be equal to negative K dt dx at x equals negative L. And then I'd have another boundary condition that looks really similar. H, okay, so looking at that blue convection arrow on the right-hand side, I'm beginning of the arrow, end of the arrow. So T at x equals L minus T infinity. And that's going to be negative K dt dx at x equals L. Perfect. That looks kind of annoying, right? I like seeing things that have a 0 in them, but you know, there you go. And I'm putting it in 2 ways because what if I wasn't thinking and I was like, I'm just going to draw all the arrows going to the right? It doesn't really matter. I'm recognizing that there's going to be heat transfer because there's a temperature gradient, but it doesn't matter. So let's do that. So Q convection here, Q convection here. All right. We'll zoom in here. Well, what's going in has to go out. Going in, going out. So this is going to be my Q by conduction at x equals negative L. This is my Q by conduction at x equals L. And if I apply my boundary conditions or define my boundary conditions, I got 2 of them. Let's make this better. I got 2 of them. First one. All right, so I have H. And remember, I'm on the left-hand side at x equals negative L. So it's at the beginning of the arrow to the end of the arrow. So T at x equals negative L minus T infinity. Actually, let's leave this over here. Equals negative K dt dx at x equals negative L. Got another boundary condition as well on the right face. So H at T at x equals L minus T infinity. Did I screw something up? I did screw something up. Somebody was like, what? She just said it. I'm sorry. Zoop. I just said it. I am sorry about that. Going back to the left-hand side again. At the beginning of the arrow, right there, would be T infinity. Sorry about that. So this is T infinity minus T at x equals negative L. Sorry about that. All right. And then this is negative K dt dx at x equals L. Again, so you could see the difference between those, but it's not going to matter. The math would work out as long as you drew your diagram. You know, you calculating a negative Q or a negative heat flux is just going to tell you, oh, my arrow should have been flipped the other way, and it would have been fine. All right. Again, this is still not taking advantage of thermal symmetry. What would take advantage of thermal symmetry is if I took both of these guys right here, and I said, okay, well, not both of these guys. If I said, let's actually just solve for half. So instead of looking at a plane wall that's a thickness of 2L, let's look at one that is just a thickness of L. Right? I know it sort of doesn't look like it's half of it, but it's half of the width of what I had before. And the way that I'm going to deal with that is I'm going to model it like there's some insulation here. All right, still have that Q dot going on there, and still my temperature distribution is going to look like that. Still got some convection over here. But now the math is going to be a lot easier because I'm going to have a boundary condition with a 0 in it, and that always makes the math easier. So my first boundary condition is going to be that, well, at x equals 0, and I know I don't need to have that k in there, but I'm leaving it there just so it's absolutely obvious that, you know, I'm applying Fourier's law, but if you leave that out, that's fine. So at x equals 0, I'm treating that as an adiabatic surface, so the whole thing is equal to 0. And then now, yes, I have a convective boundary condition at x equals L, but that's fine. So this would be negative k dt dx at x equals L, right? That represents this guy. And then I've got a convective heat flux out that way, which would be H times T at x equals L minus T infinity. So again, it's just going to make the math much simpler. We also take advantage of this when we talk about, we look at cylinders. Okay. And you know, you notice that there was thermal symmetry in this guy. You see a Q dot there. It's usually with heat generation that we're taking advantage of this thing. So for a cylinder, here's my cylinder. And yes, I have Q dot. Okay, there's the mid one. So I don't have a plane that I could draw an adiabatic surface at, but what we do is we say that there is no heat transfer, the boundary condition that we have, and let's say, by the way, let's say we've got convection on the outside, and it's that way all the way around. Right? So the two boundary conditions that I would use here, first one would be taking advantage of thermal symmetry. And the way that we do this is, remember, thermal symmetry is because you've got the same thing going around all the way around, right? And so as you move outward along that radial direction, it doesn't matter where you are, right? What angle that you're looking at along that cross-sectional area, the temperature is going to be the same, right? At this R, the temperature is this temperature. At this R, it's going to be this temperature, right? So you've got symmetry all the way around. So that first boundary condition is that, all right, negative k dt dr, because we're in cylindrical coordinates, that's Fourier's law in cylindrical coordinates. This guy is 0, right? And that's at r equals 0. That's also important, at r equals 0. Or you could just write it as dt dr at r equals 0 is equal to 0. That's fine too. And then you'd have another boundary condition for that, for the convection. So you'd have, all right, so I've got my, yes, you have conduction. And you have convection. And so this would be conduction and convection at R equals R, big R, right? So if we said this distance right here, I'm going to use this as a big R just to indicate that it's the outer radius. So this would be, right, so it's at the beginning of the arrow. So T at R equals that outer radius minus T infinity. Oops. Here we go. And that's going to be equal to negative K dt dr at R equals the big R. All right. All right. So it seems kind of awful, but let's work a problem. It's not that bad. Let's tell ourselves it's not that bad, so it's not that bad. All right. So I am going to kind of skip around with the problems. I'm going to go, just bear with me, I'm going to go to problem 20. So I'm going to kind of skip over these. I'm coming back to them. We'll come back to them, but I do want to skip over them for now. Let's go to problem 20. And that way we'll at least get a chance to be able to apply some of this stuff while it's kind of fresh in our head. All right. So we have a large plane wall. All right. So here we go. I think I want to add something, by the way. I'm going to find something else. But let's go ahead and at least draw things out so we're got it. All right, so there's my plane wall. We have a thickness of 0.2 meters. It's got a thermal conductivity of 1.2 watts per meter degree Celsius, and a surface area, so the surface area being this guy right there, this surface area is 15 meters squared. Two sides of the wall are maintained at different temperatures. So one's at 120 and one's at 50. So the 121 I'm going to put on the left-hand side, just so that when I calculate a Q, it'll end up being a positive number because it's going in the direction of increasing X. And so, yeah, so this temperature, we called it T1. It doesn't matter. I'm going to call him, this is T at X equals 0. He's 120 degrees Celsius, or you could have drawn T1. Right? And here's my T at X equals L. He's 50 degrees. Put my L here. L is 0.2 meters. Okay. So I want to find the temperature that's 0.1 meters from the wall, so halfway through. I also want to find the rate of heat conduction, but I want to add, just in general, I want to get the temperature distribution. So I want to find a specific temperature, T at X equals 0.1 meter. I want to find the rate of heat conduction if it's steady state. I'm going to cross this out and just put a little, just assume it's steady state. Okay. Rate of heat conduction. And I just want to get the general form of the temperature distribution. That's it. All right, so as far as my assumptions go, I'm going to go ahead and put steady state on there. All right, and so now let's start solving for this guy. And I'm just going to start solving for that temperature distribution. All right, so in order to do that, I need to apply my heat diffusion equation. So let's do that. All right. All right, so I've got the second derivative of temperature with respect to x. Same with respect to y. Same with respect to z. Okay. Plus, get a q dot over k equals 1 over the thermal diffusivity. And I've got the partial of the temperature with respect to time. Okay. So some of these things I'm going to go ahead and cross out because if I'm assuming it's steady state, that last term is going to go away. There's been no indication that this has any energy generation, so I'm going to go ahead and cross that guy out. Maybe I want to throw that in my assumptions that this q dot is equal to 0. And then I don't really have a temperature gradient defined in the y or the z direction, so I'll ignore those two as well. So I've only got that one term, and since it looks like temperature is only dependent in the x direction, I can get rid of that partial derivative and just make this, and I'm going to go back just to black. This would be second derivative of temperature with respect to x. All right, actually, before I set this guy equal to 0, I'm going to give myself a little bit of room because I need to integrate it. So let's go through that process. So we're going to multiply both sides by dx. And then we integrate. Zoop, zoop. All right. So the integral of 0 is just some constant of integration. I'll bring him over here. dt dx is equal to some value c1. That's what I've got when I integrate. And I'm going to do the same thing again. I'm going to multiply both sides by dx, and I'm going to integrate one more time. Right? And so now, oops, should get t as a function of x. So it's going to be c1x, but I've got another constant of integration as well. So that's my general. I'm just going to kind of highlight it. So that's my general solution. Okay, so if I ask you on a test for a general solution, that's what I'm looking for, the general solution. The particular solution is going to be the one where you have the C1 and C2 solved for, and the way that we solve for those is our boundary conditions. I know that I need 2 boundary conditions because I have 2 constants of integration. Perfect. So 2 constants. 2 boundary conditions needed. All right. All right, so first boundary condition, and I kind of already got it, don't I? I sort of wrote it on my diagram up there. I've got a constant surface temperature. So, all right, 120 degrees is the temperature at x equals 0. And looking at my general solution, that would be C1 times 0 plus C2. And so C2 ends up being 120, yeah, 120 degrees. Perfect. Highlight that guy, that's kind of nice. All right, second boundary condition. And notice, I mean, it may be working from left to right, seems maybe that's why I picked that 120. But anytime that you've got a boundary condition where something is equal to 0, whether it be the coordinate or the fact that, I don't know, P transfer is 0, apply that boundary condition first, because then your math is going to work out much better, much better. So, all right, then we've got the other one, x equals L. That's 50 degrees. So x equals L, and that's going to be C1L plus C2, or C1L plus, I already figured out what C2 is, 120 degrees Celsius. All right, so looks like C1 is going to be 50 degrees Celsius minus the 120 degrees Celsius over L, which was 0.2 meters. So I end up getting a value of negative 350, and it's degrees Celsius per meter. Perfect. All right. All right. Perfect. All right. So, I mean, yeah, I guess it's not really absolutely necessary, but if I want it, why are you not? Are you being super annoying? I guess I could plug it in. Why are you? There we go. All right. So I guess if I wanted a, you know, an answer for for part C, which why wouldn't you? There we go. There it is. And so I guess it's really easy to figure out t at x equals some particular coordinate, because you just plug it in. All right. So I've got 85 degrees Celsius. Okay. This one's really easy because, well, what you'll notice about that temperature distribution is that it's linear, right? You've got, I mean, that's clearly an equation of a line, right? An equation of a line being y equals mx plus b. I mean, that's what that is. So when I look at the temperature distribution, if I wanted to draw it, it's going to look like this. It's going to look like a line all the way down to x equals L. Maybe I should have like drawn it all the way down to x equals L, but it's going to be a line, right? All right. Very last thing I wanted to do was find Q. All right, so Q, applying Fourier's law, negative K times the area, dt dx. And normally, you know, we do need to specify where we're talking about, but it doesn't matter here because it's the same all the way through. How do I know it's the same all the way through? Because dt dx is equal to, where is it? dt dx is equal to C1, which is a constant. So negative K times A times C1, negative K, A, well, we're given all those numbers, so it's just plug and chug, right? Negative 1.2 times 15 times negative 350, we end up getting 600 and, or 6,300 watts. There we go. Perfect. Okay. Let's work another one. Do I need to go back? Maybe it's okay. All right, I'll go on to the next one. All right, so we have one side of a plane wall is maintained at some temperature 100 degrees. The other side is exposed to a fluid at 10 degrees Celsius. So I'm going to pick the one on the left-hand side at x equals 0 to be the hot side. Just, oops, just so that, you know, when I calculate a Q, it's going to be positive because it's going in the direction of increasing x. All right, so here he is. There we go. All right. I draw my, I don't like that. That's too light. All right, so there's x, 0. There's L. L is given to me 40 centimeters, so 0 0.04. All right. Actually, no, I'm sorry. Stupid. There we go. All right. So on the left-hand side, zoop. All right, so that surface, and I'm gonna get rid of, I'm not gonna write TS because then it's like, what surface are we talking about? There's two of them. Let's just call it T at x equals 0. That's 100 degrees Celsius. And then the other side again is exposed to convection. So the temperature of that fluid is 10 degrees Celsius. The convective heat transfer coefficient is 10 watts per meter squared degree Celsius or per meter squared Kelvin. We've got a thermal conductivity of the wall given to us as well. So K is equal to 1.6 watts per meter Kelvin or meter degrees Celsius. Go. Or meters. Watts per meter Kelvin, that would be fine too. And we want to find the heat flux from the wall to the fluid. And let's throw something else on there. Let's go ahead and get the temperature distribution because why not? So let's say we want both. Okay, so I'm going to say first we're going to find that temperature distribution. You know, we're on a roll. Let's do it. And we're going to find the heat flux from the wall to the fluid. So what I'm looking for, to tell you the truth, is this guy. So this guy is my Q by convection, and that's what I'm looking for. Okay, we want it in terms of flux. All right. All right. So let's go ahead. We're not given any information about how things are changing with time, so let's put that as it is. Perfect. Don't have any indication that there's any Q dot. Yeah. And seems to be one-dimensional. So actually, I'm gonna put my solution up there. All right. All right, so heat diffusion equation, you'll see that it's going to simplify pretty much like what the previous problem did, but I'm going to write it down anyway because I like to write everything down. So here we go. Partial with respect to x, partial with respect to y, partial with respect to z, plus, if we had any heat generation, we'd put that one there, and then the transient effects are going to be on the other side of that equal sign. But of course, steady state, we're modeling in a steady state, no indication of any heat generation, and there is no temperature gradient defined in the y or the z direction. And the fact that it says it's a plane wall is indicative of one-dimensional heat transfer. All right, so same thing. Set this guy equal to 0, integrate it, So you're going to get dt dx is equal to c1, integrate it again, and you're going to get t as a function of x is equal to c1x plus c2. So I mentioned in the previous problem, this guy right here, this guy is what's called the your general solution. This is your general solution. This guy that guy is your governing. It's the governing equation. Yeah. So this is your simplified governing equation. All right. Yeah. All right. What is the assumption with Q dot? So my assumption with Q dot, is that it's equal to 0. I'm sorry. All right. And so now I just need to, yep. So now I just need to look at those boundary conditions. So first one is at x equals 0. So I'm going to pick that one first and apply that because, again, anything with a 0 in there makes life easier. So first boundary condition is that t at x equals 0 is equal to 100 degrees. And that's equal to C1 times 0 plus C2. So I can see that C2 has got to be equal to that 100 degrees Celsius. Perfect. So I'm gonna highlight that because that's useful. All right. Next boundary oops. This one. All right. Next boundary condition. So it's a convective boundary condition, and it's going to be defined at x equals L. Okay. So I know if I did a surface energy balance at x equals L, whatever is going out has to be coming in, right? And vice versa, right? So whatever's going in has to be going out. So I could also define a Q by convection or a Q by conduction here at x equals L. So I would just say, all right, well, great. Negative K dt dx at x equals L is going to be equal to Q by convection, which is H times T at that surface, which is x equals L, minus T infinity. All right. So now I have to evaluate dt dx, which it doesn't matter if I'm evaluating it at x equals L or not. It's just equal to C1, which is 100. I'm sorry, it's just equal to C1. We haven't solved for C1 yet. So this would be negative K times C1, right? And then this is equal to H times T at x equals L, which is going to be C1L plus C2 minus T infinity, right? So that's T evaluated at x equals L. Yes, I know what C2 is, and that's fine. So this is going to be negative AC1. Well, I guess I'm going to actually just delete that. Yeah. So let's look at what I know. So I know T infinity. I know C2. I know L. I know K. K was given to me as the 1.6 number. And so, and I know H. That's given to me as well. So I just need to solve for C1. So my C1 ends up being negative 160.7, not watts, sorry, degrees Celsius per meter. There we go. All right. And, and you could plug it in, honestly, on a test if you're kind of running out of time and I asked you for the for the, the particular solution for the temperature distribution. If I asked you for the temperature distribution, you know, having this, and this is enough to tell the story for me. But if you like having something written out, that's fine. So this would be negative 160.7 degrees Celsius per meter times x plus 100 degrees Celsius. There you go. Done. I'll put that in a happy cloud. Okay, so that was A. Right? And then B, all B is going to tell me is, all right, so I need to define the Q by convection. I mean, that's kind of this guy right here. So I could either plug in, I could either evaluate the right-hand side of that equation or the left-hand side. And I think the left-hand side is actually a little bit easier, right? Because this would be just negative K times C1. But I end up getting 257 watts per meter squared. Alrighty. See. All right, so let's go back. We'll go back to problem 16. Maybe we'll do problem 17. We'll see what happens. All right, there we go. All right, so problem 16 is kind of going backwards a little bit as far as, the complexity of what we've been doing. Because with this one, it looks like they are already giving us the temperature distribution. So, but it's okay. Because, by the way, on your test, you're going to have 5 conceptual questions. I mean, I've mentioned this before, but I'll give you a little bit more detail. Like the homework. And I'll post a video. So video posted Friday of those solutions. Just kind of walking through why they're right, or why the answer is the way that it is. So 5 conceptual questions, and then you have 2 work it out problems. So first problem would be like the questions through, say, number 19. And then one problem like 20 through I think I've got 4, so 20, 21, 22, 23, where you need to apply that heat diffusion equation apply boundary conditions and solve for the temperature distribution. And you'll either do it as a function of x or r. So we'll do two two types. Tomorrow we'll go over cylindrical coordinates. So hopefully that gives you a little bit more kind of thinking about where you should focus your energy on. Anybody have any questions about that? Okay, I will assume maybe not. Okay, so let's go to our problem. I'm sorry, people are probably writing. So problem 16. So we have uniform internal heat generation. We're given a Q dot. Is occurring in a cylindrical nuclear reactor fuel rod of 50 millimeters in diameter under steady state conditions. So I'm going to go ahead and write that down. Right. So there it is. I do have Q dot. So Q dot is 5 times 10 to the 7th watts per meter cubed. All right. And the diameter, gray. So my diameter is 50 millimeters. Steady state. So I'm actually going to put I'll put the assumptions. We'll put that guy over here. So steady state. And then we're given what the temperature distribution is. So the temperature, and it's going to be a function of R, and it says R is in meters. So I probably need to put this 0.05 meters. So it's A plus B R squared. So they've already done kind of the hard work. And they've got these guys. They've already solved for those constants. So they've already gotten that temperature distribution and solved for their constants of integration. So they've already done that legwork. All right. We're given some properties. So we were giving given rho, the density, the thermal conductivity, and the specific heat. And we want to find the rate of heat transfer per unit length. So what we're looking for, don't like that one. What we're looking for is Q per unit length. All right. Oh, and I want this at R equals 0 and Q over L at R equals R. Okay, big R being half of the diameter, 0.025 meters. All right, so let's keep going. All right. So I know that Q over L, regardless of whether I'm if I'm looking at R equals 0 or R equals that outer perimeter, I'm going to need to integrate. So 1 over L, not integrate. I'm going to need to apply Fourier's law. So this is negative K times the area times dt dr at R equals 0. However, I'm going to make a note here. This is exactly the scenario that we looked at just a hot second ago. Right? Good, it's right there. So we could take advantage of thermal symmetry here because we do have a thermal symmetry. Now, I didn't define a convective boundary condition. Um, However, I can see based on this temperature distribution that I do have thermal symmetry because it, for a given R, it doesn't matter. So like, let's say you're looking at this, say this is all at the same R. It doesn't matter whether I'm looking right here or here or here. If I plug in that R value, I'm going to have the same temperature. And so that temperature distribution is symmetrical all the way around. And so, well, this guy is just going to be 0. How come? Because thermal symmetry. Right? Also, right, dt dr at r equals 0 is equal to 0. All right, so I'm going to call, let's call this A and call this B. Okay, there's A. Now I got B. All right, so I'm going to do the same thing. Q per unit length, but this time I'm defining at R equals big R. All right, so this is 1 over L, and I'm going to define it here. So this is going to be negative K times an area dt dr, all at R equals that big R. All right, so a couple of things. The area, well, the area that I'm looking at is going to be the area on the outside of this thing, right? So the area is going to be the perimeter, pi d, times the length. All right, so I have 1 over L times negative K times the area, so pi dl. So look at that, it didn't even matter that I didn't know the length. If we were worried about that, it wouldn't even matter. And then we've got to take the derivative of the temperature with respect to R. And I've got my temperature with respect to R up there. All right, so this would be dt dr, so it would be 2br. But of course, it wouldn't be a lowercase r. I'm defining it at a very, I'm defining it at a very specific r, right? The outer radius. Okay. And I've got the outer radius is 0.025. So yeah, let's plug some stuff in. What was the K value? K was 30. So I have negative 30 watts per meter Kelvin. Oops, and you know what I just noticed? There's going to be a negative because that B's got a negative in there. Times pi times d. See? Yeah. So 0.05 meters. And then I've got 2 times r, which would also be 0.05. 0.05 m. And then my B is the negative 4.167 times 10 to the 5th degrees Celsius per meter squared. All right, so it looks like, just kind of look at the units that I'm going to get here. So meter squared, meter squared. Yes, I know that this is, I got a Celsius up here and a Celsius down here. It does not matter because I could put this in watts per meter degree Celsius, and remember that wouldn't change because they're defining it per unit degree change. So this goes away and this goes away. And so the final units are going to be watts per meter, which is exactly what I thought that I would end up with. or what I should end up with. Right, so I end up getting 98,132.85, and that's watts per meter. Perfect. Awesome. Right. All right.
Are D and R the same in this? D and big R?
No, but 2 times R would be the same thing as D. Right, so this is 2R, and that guy is R. That good?
Oh, I see.
Yeah. Sorry about that. Okay. All right. Let's do a more conceptual, or not conceptual, but kind of sort of a conceptual thing. So I'm gonna skip 17. I'm gonna go to 18. Just feeling it. Just so we sort of have a general feel for temperature distributions and what it looks like. All right, so problem 18. You have temperature distributions within a series of one-dimensional plane walls at an initial time at steady... At an initial time, at steady state, and at several intermediate times are shown. So I'm going to zoom in on one of these. So at time 0, right, because it says at an initial time, there we go, and then it said at steady state, this is steady state as t goes to infinity, and then at several intermediate times. So that's the verbiage, what that means. But we need to find, we want to write for each case, we want to write the appropriate form of the heat diffusion equation. And we want to write the equations for the initial condition and the boundary conditions that are applied at x equals 0 and x equals L. If volumetric generation occurs, it's uniform throughout the wall and the properties are constant. So we're going to analyze each one of these cases, but I'm going to just, in general, I'm going to apply my heat generation equation. So I have second partial derivative with respect to x, with respect to y, and with respect to z, plus generation term, if it's, if we have any. All right. Perfect. And so the only thing that I can kind of simplify for all of these is that, well, they're all plane walls. So I'm going to go ahead and at least cross this guy out and this guy out. All right. And I'm going to actually move it down a little bit. So I'm going to have, it's probably hard to see, but this is case A, case B above it, case C, and case D. All right. So I'm going to have a column for case A. Case B, C, and D. I might want to move this all down, and I'm sorry. Yeah, maybe it's okay. So we're going to put our governing equation here. Our governing equation being that kind of simplified differential equation, but we haven't solved for it yet. Okay. We haven't solved for the temperature distribution. It's just the general governing equation when we cross out as many terms out of that heat diffusion equation as we can. All right, then we're going to have an initial condition. So IC initial condition. Then we're going to need two boundary conditions. So boundary condition number 1 and boundary condition number 2. Okay. I should put a little thing on top of that just to make it. Okay, there we go. Not that pretty, but it's okay. All right. It's semi-organized, I suppose. All right, so let's handle that first one. See what's going on. All right. So if I look at this guy. All right, so I've got one boundary condition that seems to be pretty darn obvious, and that's that I don't have any heat transfer right there. So I could say dt dx at x equals 0 is 0. And I'll throw that in my chart. All right. So, all right, so initially at t equals 0, that's my initial condition. And so I think, let's go ahead and at least put that in here. So my initial condition is t at x equals 0. It's just some t initial. I don't know. I don't know what it is. And you know what? It's going to be the same for every single other case, because if I look at it, they've all got a t at x equals 0, t at x equals 0 at some temperature, right? For A, it was low. For B, it was high. Yes, I hear you. For C, it's low again. Yeah, for D, it's low again, but it doesn't matter. It's just some initial condition. So I'm going to put that in here. So for A, for B, it's a green line. Sorry about that. All right. So T x equals 0 is T initial, whatever that is. T at x equals 0 is equal to T infinity, whatever that is. T at x equals 0, did I say T infinity? I didn't mean to. Equals T initial. Again, whatever that is. All right. And then I had already figured out that that first boundary condition was going to be that you had an adiabatic surface. In fact, if I look at every single one of those, they all have an adiabatic surface at x equals 0. So that makes things really simple, doesn't it? Well, let's look at that. Let's go ahead and put that at least for all those boundary conditions. So dt dx at x equals 0 is 0. Same thing. If you have the ability to copy paste, feel free. I won't, just so that I can kind of gauge how long it's going to take for everybody to write it down. So all that's equal to 0. Oops. All right, perfect. All right, so I'm still missing some information, missing the second boundary condition, and also missing, whatever simplification I have to do for these, for my governing equations. So All right. All right, so let's go back to that first one. So what's happened here, this is analogous to having some convective boundary condition. So I'm just going to go ahead and tell you that up front, and then let's walk through it and see how that makes sense. So if I had, I guess really I should make this, maybe I should make that, it's a high temperature, right? T infinity H. So I've exposed it to some hot fluid, and the temperature distribution, and that's what's indicated by those little lines that are kind of going up. That's what's indicated there. So the temperature, it starts out low, but then at intermediate times it's going up. But of course it's going to be higher closer to that hot fluid than it is at x equals 0. It's going to take a little bit for the temperature to come up at x equals 0. Okay, so at this time, okay, x, sometime after 0, okay, here it is. Oh, a little bit later, temperature is coming up a little bit more closer to that wall, coming up a little bit more closer to that wall, until finally, as time goes on and on and on, at some point they reach steady state conditions, right? So at some point, the temperature of that wall will come into equilibrium throughout with T infinity. So I am actually gonna kind of clean that up a little bit because I wrote all over it, but that's what's going on there. And not only that, it's come to some constant temperature throughout, so there's no heat generation causing some weird temperature distribution within there, right? So now all I have, oops, so I've got my governing equation as well, because in this first case, there's no Q dot going on. So my governing equation is the second derivative of that temperature with respect to x is equal to 1 over thermal diffusivity, first derivative with respect to time. Okay, and then of course, again, I do have a convective boundary condition going on. So at x equals 0, I would say, x equals L, I would say that the convection here, or conduction here, has to be equal to the convection at x equals L as well. So I'd have negative K dt dx at x equals L is equal to the convection. So H T at x equals L minus whatever that T infinity is. So what was telling us that I had no heat generation? It's because that temperature distribution, the temperature distribution is flat as that time goes to infinity. Right? Basically, the entire wall is coming to some temperature, and you don't have any thermal energy generation causing, like, maybe towards the wall being at a higher temperature than the temperature at x equals L. So that makes things, with that kind of thought there, that makes it probably pretty easy. Let's look at the other ones. So A, B, C, and D. So I'm going to highlight as T goes to infinity. There's a 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 T goes to infinity. So you can see that in case B, absolutely I have heat generation. I have a Q dot. For part C, or for C, nope, that's flat, no Q dot. And for the very last one, for D, I do have thermal energy generation. So go ahead and at least fill in the governing equation spots. All right, so B, I have it, and D, I have it. B and D. Okay. And then it's the same thing for D. In fact, I'm gonna copy it and bring it on down there. Perfect. And then the other one for C, because as T goes to infinity, that temperature distribution was flat. I don't have any. No volumetric heat generation. All right. So let's look at those other boundary conditions because that's the only other thing I got. All right. So, all right, so let's look at B. See what kind of boundary condition we've got. So you can see at x equals L, I have one temperature. There's only one possible temperature. Even starting at x equals 0, all the way till I run out the clock, the temperature at x equals L is always some constant temperature. So I'm going to call that temperature, I'm going to say this temperature, T at x equals L, is just some surface temperature. Okay. And that's it. That's it. Some constant temperature, whatever it is, whatever that may be. And it looks like, let's see. Ooh, actually. Ah, you know what? That's actually the same thing. We messed up. I say we, because nobody said anything. I'm just kidding. It was all me. That is actually the same case that we've got going on in A, so I actually need to fix that. Yeah. There we go. T at x equals L is equal to some constant surface temperature. I'm sorry, guys. I'm sorry. It's the end of the day. Let's blame it on that, yeah? So for A and B, the second boundary condition is a constant surface temperature. So fix that. Let's go fix that, okay? Ooh, oh my goodness. So I'm sorry. I'm going to delete this. I do apologize. Do apologize. So T at x equals L is equal to some constant temperature. We'll call it TS. T at x equals L equal to some constant TS. So if I've screwed you up and you need me to talk through that again, please let me know. All right. I think we're about ready to call it a day. We're going to get the other two boundary conditions and then we're going to be done, okay? Okay. All right, so I'm going to zoom in on these other guys. So you can see for C and D, that temperature at the surface is changing as time goes on. That is a convective boundary condition. So both of those have convection. It's the same boundary condition. A bonus. Okay, so here we go. So this would be negative K dt dx at x equals L is equal to h at t x equals L minus t infinity. Oh my goodness. And it's the same thing for that last one. Oh man. Yeah, my head's shot. It's pajama time, yeah? All right. So we'll call it there. If you do have questions, I'll hang out for a little bit if you have any questions, but I'll go ahead and I think I'll end the stream on YouTube. If you do have questions, just pop on over to Zoom and I'll be here for a little bit. All right. Thank you guys. Appreciate it. Y'all have a wonderful night. I'll take my picture off here. Thank you guys.